Somewhere in the center of our galaxy, roughly 26,000 light-years from where you are lying right now, there is an object called Sagittarius A. It is a supermassive black hole. It contains the mass of 4 million suns, compressed into a region of space smaller than the distance between the Earth and the Sun. It has been there for billions of years. It will be there for billions more. And for most of its existence, it has been almost perfectly still. A vast, patient darkness at the heart of the Milky Way, around which hundreds of billions of stars, including our own Sun, slowly orbit. Right now, as you lie still in the dark, our entire solar system is moving through space at approximately 230 kilometers per second, completing one orbit around this distant black hole. One orbit takes roughly 225 million years. The last time we were in this position in our orbit, the dinosaurs had not yet appeared on Earth. We are all slowly circling a black hole. Tonight, we are going to spend time with black holes, not as objects of fear, but as objects of wonder. Because black holes are perhaps the most extraordinary things the universe has ever made. They are places where space and time behave in ways that defy every intuition we have built up in a lifetime of living in the ordinary world. They are places where matter has been compressed to such extremes that the very fabric of space-time curves completely in on itself. Where time slows down and light cannot escape. Where the laws of physics, as we understand them, reach their absolute limits. And something new, something we do not yet have the mathematics to fully describe, takes over. They are the universe's deepest mystery. And they are everywhere. There are thought to be hundreds of millions of stellar black holes in the Milky Way alone, the remnants of stars that lived and died long before our Sun was born. And at the center of almost every large galaxy in the observable universe, including our own, sits a supermassive black hole of almost incomprehensible size and mass. The universe is full of darkness. And that darkness is full of wonder. Let your body settle. Let your breathing slow. We begin at the beginning, with the death of a star. To understand a black hole, you first have to understand a star, because every stellar black hole begins its existence as a star. And a black hole is, in many ways, the final chapter of a star's long and luminous life. A star is a battle. For its entire existence, which may last millions or billions of years depending on its size, a star is engaged in a continuous tug-of-war between two forces. Gravity pulls inward, trying to compress the star's enormous mass into a smaller and smaller space. And the energy produced by nuclear fusion in the star's core pushes outward, resisting that compression, keeping the star inflated and burning. For most of a star's life, these two forces are in perfect balance. The star burns steadily, its outward pressure exactly matching the inward pull of gravity. Our own Sun has been in this balance for approximately 4.6 billion years and will remain so for roughly another 5 billion years. But eventually, the fuel runs out. In the core of a star, hydrogen atoms are fused together to form helium, releasing enormous amounts of energy in the process. When the hydrogen is exhausted, the star begins fusing helium into heavier elements: carbon, oxygen, neon, silicon. Each new fuel source provides less energy and lasts for a shorter time. In a massive star, one significantly larger than our Sun, this process of fusing progressively heavier elements continues until the core is made almost entirely of iron. And iron is where fusion stops. Unlike lighter elements, fusing iron absorbs energy rather than releasing it. The outward pressure suddenly vanishes. What happens next takes less than a second. With nothing to resist it, gravity wins instantaneously and completely. The outer layers of the star, which may contain more mass than several suns, collapse inward at a significant fraction of the speed of light, crashing into the iron core. The resulting shock wave is so violent that it blows the star apart in an explosion called a supernova, one of the most energetic events in the universe. For a brief period, days or weeks, a single supernova can outshine the entire galaxy it belongs to. Billions of stars outshone by one dying sun. And what remains at the center after the explosion has swept outward into space depends on how massive the original star was. For stars of moderate size, what remains is a neutron star, an incredibly dense object the size of a city, made almost entirely of neutrons packed together as tightly as the laws of physics allow. But for the most massive stars, those that began their lives with perhaps 20 or 30 times the mass of our Sun, not even neutron pressure can resist gravity. The collapse continues. The core is compressed further and further, past the density of a neutron star, past any density we can directly observe or measure, until it reaches a point of infinite density. A singularity. A black hole has been born. A black hole is not, despite its name, simply a hole in space. It is an object, an extraordinarily dense concentration of mass, with a specific structure, specific properties, and a boundary that separates it from the rest of the universe. That boundary is called the event horizon. The event horizon is not a physical surface. There is no wall, no membrane, nothing you could touch or see. It is simply a threshold, a point of no return. The event horizon marks the distance from the black hole's center at which the escape velocity, the speed you would need to travel to escape the black hole's gravity, equals the speed of light. Since nothing in the universe can travel faster than light, anything that crosses the event horizon cannot escape. Not matter, not energy, not information of any kind. Once something crosses the event horizon, it is, from the perspective of the outside universe, gone. This is why black holes appear black. It is not that they absorb light in the way a dark surface absorbs light. It is that any light falling toward the black hole and crossing the event horizon simply cannot return. The black hole emits nothing. It is a perfect absence of light in the fabric of space. The size of a black hole's event horizon, called the Schwarzschild radius, is directly proportional to its mass. For a black hole with the mass of our Sun, the Schwarzschild radius would be approximately 3 kilometers. Our entire Sun, with its diameter of 1.4 million kilometers, compressed to a sphere 6 kilometers across. For comparison, the event horizon of Sagittarius A star, the supermassive black hole at the center of our galaxy, has a radius of approximately 12 million kilometers. That is roughly 17 times the distance from the Earth to the Sun. An event horizon so large that the entire inner solar system could fit inside it. Beyond the event horizon, deeper still, lies the singularity. This is the point at the center of the black hole where, according to the equations of general relativity, the density becomes infinite and the curvature of space-time becomes infinite. It is a point where our current understanding of physics breaks down completely. Where the equations that describe the universe so accurately, everywhere else produce results that cannot be physical. The singularity is not a place we can observe or visit or measure. It is, in a sense, the edge of what physics can currently say. What actually happens there, what the true nature of the center of a black hole is, remains one of the deepest unsolved questions in all of science. The universe keeps its deepest secrets well. At the center of almost every large galaxy in the observable universe, including our own Milky Way, sits a black hole of almost incomprehensible mass. These are supermassive black holes, and they are among the most mysterious and awe-inspiring objects in the cosmos. Stellar black holes, the kind formed from the collapse of individual stars, typically contain between a few and a few dozen solar masses. Supermassive black holes are different by orders of magnitude. The smallest known supermassive black holes contain perhaps 100,000 times the mass of our Sun. The largest known, a black hole at the center of a galaxy called TON 618, contains approximately 66 billion solar masses, 66 billion suns worth of mass, compressed into a single object. The event horizon of TON 618 has a radius of approximately 1,300 astronomical units, 1,300 times the distance from the Earth to the Sun. Our entire solar system, out to and including the distant Oort cloud, could comfortably fit inside it. How supermassive black holes form is one of the great open questions of modern astrophysics. They are too massive to have formed from the collapse of a single star. One theory suggests they grew from smaller seed black holes that merged and accumulated mass over billions of years. Another suggests they formed from the direct collapse of enormous clouds of gas in the early universe, before the first stars had even formed. What we do know is that they are ancient. The oldest known quasars, the extraordinarily luminous objects powered by supermassive black holes actively consuming matter, date to less than 1 billion years after the Big Bang. Supermassive black holes were among the first complex structures to form in the universe. In 2019, the Event Horizon Telescope, a global network of radio telescopes working together as a single Earth-sized instrument, produced the first ever image of a black hole. The image showed the supermassive black hole at the center of a galaxy called M87, 55 million light-years from Earth. It appeared as a bright ring of glowing gas surrounding a dark central shadow. The black hole's shadow cast by the bending of light around its event horizon. It was the first time humanity had directly observed one of the universe's most extreme objects. A dark circle surrounded by light, 55 million light-years away. A photograph of the edge of the unknowable. The image was exactly what Einstein's equations had predicted it would look like, a century before it was taken. One of the most extraordinary things about black holes is what they do to time. According to Einstein's theory of general relativity, time does not pass at the same rate everywhere in the universe. The stronger the gravitational field, the slower time passes. This is not a metaphor or an analogy. It is a measurable, experimentally verified physical fact. Time itself flows at different rates, depending on how close you are to a massive object. This effect, called gravitational time dilation, is real enough that the GPS satellites orbiting the Earth have to account for it. Because the satellites are further from the Earth's center of gravity than we are, time passes very slightly faster for them than for us. If this difference were not corrected for, GPS systems would accumulate errors of kilometers per day. Near a black hole, this effect becomes extreme. Imagine watching a clock as it falls toward a black hole. From your position far away, you would see the clock slow down as it approaches the event horizon. The closer it gets, the slower it ticks. As it approaches the event horizon itself, it appears to slow almost to a stop. Frozen in time at the threshold, the light from it becoming increasingly red-shifted and faint. From the perspective of someone riding the clock toward the black hole, however, nothing unusual happens at the event horizon. They cross it without noticing any particular moment of strangeness. Time, from their perspective, continues to flow normally. This is one of the deepest paradoxes of black hole physics. The same event, the crossing of the event horizon, appears completely different depending on where you are observing from. For the outside observer, the infalling object is frozen forever at the threshold. For the infalling object itself, nothing marks the crossing at all. Time near a black hole is not simply slow. It is relative in a way that our everyday experience of time gives us no intuition for. The novelist and essayist might say that time near a black hole is like the border between sleeping and waking, where each side experiences the transition differently, and what is an instant from one perspective is an eternity from another. There is a thought experiment in physics called the twin paradox. If one twin travels near a black hole and returns, they will find their sibling has aged far more than they have. Years or decades may have passed on Earth, while only months passed for the traveler near the black hole. They would return to a world that had moved on without them, their body younger than it should be, their twin old. Time, near a black hole, is generous to the traveler and merciless to those left behind. Let us imagine, gently and slowly, what it would be like to fall toward a black hole. Not to be frightened by it, but to follow the physics, to see what the universe's most extreme gravity would actually feel like from the inside. From far away, a stellar black hole would be invisible. You would know it was there only by its gravitational influence on nearby stars and gas, or perhaps by the faint glow of an accretion disk, a swirling disk of superheated gas spiraling inward, glowing across the electromagnetic spectrum from radio waves to X-rays. As you drifted closer, you would begin to notice the gravitational influence. Not through any sensation. Gravity, after all, feels like weightlessness when you are in free fall. But through the light around you beginning to behave strangely. The black hole bends space itself, and with it, the paths that light travels. Stars behind the black hole would appear to shift position, their light bent around the black hole's gravity well. You might see multiple images of the same star, bent around either side of the black hole. You might see a ring of light, an Einstein ring, where light from a star directly behind the black hole is bent equally in all directions, forming a perfect circle of light around the darkness. As you fell closer still, the darkness in front of you would grow. The black hole's shadow, the region from which no light escapes, would expand until it dominated your field of view, a perfect circle of absolute darkness surrounded by a bright ring of bent and compressed starlight. And then you would cross the event horizon. You would feel nothing, no wall, no shock, no sensation of transition. The event horizon is not a physical barrier. You would simply be inside, with no way of knowing from local experience that anything had changed. But the universe outside would have changed for you. The exit has closed. Every path forward, through space and through time, leads toward the singularity. In the strange geometry inside a black hole, the singularity is not in a direction you can avoid. It is in your future. Just as you cannot avoid tomorrow, you cannot avoid the center. How long you would have between crossing the event horizon and reaching the singularity depends on the size of the black hole. For a stellar black hole, the journey would be very brief, fractions of a second. For a supermassive black hole like the one at the center of M87, you might have hours. Hours of drifting through the interior of a black hole, watching the universe outside compressed into a shrinking circle of light above you. The stars and galaxies of the entire observable universe, visible in that single bright point, blue shifted and crowded together. And then, peacefully, the physics we understand runs out. In 1974, the physicist Stephen Hawking made a discovery that astonished the scientific world. Black holes, he showed, are not entirely black. They glow, very faintly, almost imperceptibly. But they glow. This radiation, now called Hawking radiation, arises from a subtle interplay between quantum mechanics and general relativity at the event horizon of a black hole. To understand it, we need to think about the nature of empty space. In quantum mechanics, empty space is not truly empty. It seethes with quantum fluctuations, pairs of particles and antiparticles constantly popping into existence and annihilating each other almost instantaneously, borrowing energy from the vacuum and returning it so quickly that they leave no lasting trace. This happens everywhere in space, all the time, including near the event horizon of a black hole. But near the event horizon, something different can happen. One particle of the pair falls inside the event horizon, while the other escapes into space. The escaping particle carries away real energy, energy that ultimately comes from the black hole's mass. The black hole, in other words, slowly loses mass by radiating particles away from its event horizon. This is Hawking radiation. The effect is extraordinarily small for any black hole that could actually form from a stellar collapse. The Hawking radiation from a black hole with the mass of our Sun would have a temperature of roughly 60 billionths of a degree above absolute zero, far too faint to detect against the background radiation of the universe. But over time, over extraordinarily vast amounts of time, Hawking radiation means that black holes do not last forever. They evaporate. They slowly lose mass, becoming smaller and smaller, their Hawking radiation growing more intense as they shrink, until in the final moments they evaporate in a brief burst of energy. For a stellar mass black hole, the evaporation time is so long it defies comprehension, vastly longer than the current age of the universe. A black hole with the mass of our Sun would take approximately 10 to the power of 67 years to evaporate, a number so large that writing it out would fill many pages. But evaporate it will, eventually. In the unimaginably distant future, when the universe is so old that all the stars have burned out and all the galaxies have dispersed, the last black holes will be slowly glowing with their faint Hawking radiation, growing smaller and warmer, until in a final flash of light, they are gone. The universe will end not with a bang, but with the slow, quiet evaporation of the last black holes, leaving behind only a cold, dark, expanding void. Black holes are not simply extreme or exotic objects at the fringes of physics. They are windows, perhaps the clearest windows we have, into the deepest questions about the nature of space, time, matter, and information. One of the deepest questions black holes have raised is called the black hole information paradox. It was first identified by Stephen Hawking in the 1970s and has occupied some of the finest minds in theoretical physics ever since. The paradox goes like this. In quantum mechanics, information is conserved. The laws of quantum physics are reversible. In principle, if you know the complete quantum state of a system at any point in time, you can calculate what it was at any point in the past or future. Information is never truly destroyed. But when matter falls into a black hole, and the black hole eventually evaporates through Hawking radiation, what happens to the information contained in that matter? Hawking's original calculations suggested that Hawking radiation is completely random, that it carries no information about what fell in. The information would be destroyed. This seems to violate quantum mechanics. And since both quantum mechanics and general relativity are extraordinarily well-tested theories, having them contradict each other in this way is deeply uncomfortable for physicists. The resolution to this paradox, if it has one, likely requires a theory that unifies quantum mechanics and general relativity. Such a theory of quantum gravity, does not yet exist. It is perhaps the greatest unsolved problem in theoretical physics. Black holes are also telling us something profound about the nature of space and time themselves. The holographic principle, suggested by the study of black hole thermodynamics, proposes that all the information contained in a volume of space can be encoded on the boundary of that space, in the same way that a hologram encodes a three-dimensional image on a two-dimensional surface. If this principle is correct, it suggests that our three-dimensional experience of space may in some sense be a kind of projection, that the fundamental description of reality is two-dimensional, and the three-dimensional world we experience is in some sense emergent. This is not science fiction. It is a serious proposal by serious physicists, motivated by the mathematics of black holes. Black holes are where physics goes to find its edges. And at those edges, the universe reveals that it is stranger and more wonderful than we had imagined. Black holes do not exist in isolation. They are woven into the larger structure of the universe, connected to galaxies, to gas clouds, to the cosmic web of matter that spans the entire observable universe. The relationship between supermassive black holes and their host galaxies is one of the most fascinating areas of modern astrophysics. Despite the fact that a supermassive black hole is tiny compared to the galaxy it inhabits, the event horizon of Sagittarius A star is roughly the size of our solar system, while the Milky Way is roughly 100,000 light-years across. The two appear to have grown together, their properties deeply linked. The mass of a supermassive black hole is closely correlated with the mass of the central bulge of its host galaxy. Larger galaxies have larger central black holes in a relationship that holds across many orders of magnitude, across billions of years of cosmic history. This suggests that the growth of black holes and the growth of galaxies are not independent, that they have shaped each other over cosmic time. When a supermassive black hole is actively consuming matter, drawing in gas from its surroundings, heating it to millions of degrees as it spirals inward, launching powerful jets of energy into space, it can influence the entire galaxy around it. The energy output of an active galactic nucleus can blow gas out of the galaxy entirely, shutting down star formation across a region hundreds of thousands of light years wide. A single black hole, through the sheer violence of its feeding, can shape the destiny of an entire galaxy of hundreds of billions of stars. But most supermassive black holes, most of the time, are quiet. Sagittarius A star, the one at the center of our own galaxy, is currently almost entirely dormant. It consumes only a trickle of matter, a tiny fraction of what it would need to become luminous. It sits in its place at the galaxy's center, patient and still, its enormous gravity felt across the entire Milky Way, but its appetite currently satisfied. Our galaxy is peaceful, in part because its central black hole is sleeping. Astronomers have found evidence that Sagittarius A star was far more active in the past. Perhaps just a few million years ago, a brief moment in cosmic time, when it may have consumed enough matter to create enormous bubbles of hot gas, extending tens of thousands of light years above and below the plane of the Milky Way, known as the Fermi bubbles. The universe remembers the past activity of its black holes in the structures of gas and light that surround them, long after the feeding has stopped. To understand where black holes come from, we have to travel back to the very beginning, to the first moments of the universe, when everything that exists was compressed into a space smaller than an atom, hotter and denser than anything that has existed since. The Big Bang happened approximately 13.8 billion years ago. In the first fraction of a second, the universe expanded from that impossibly small and hot initial state into something large enough to contain the first particles of matter. In the first 3 minutes, protons and neutrons formed, and then the first atomic nuclei, hydrogen and helium, the simplest elements, which still make up the vast majority of all ordinary matter in the universe today. But the universe was not yet ready for stars. For the first several hundred million years after the Big Bang, a period cosmologists call the Cosmic Dark Ages, the universe was filled with a diffuse fog of hydrogen and helium gas, slowly cooling, slowly clumping together under gravity, with no stars yet burning to illuminate it. Then, gradually, the first stars ignited. These first stars, known as population 3 stars, though none have ever been directly observed, were almost certainly very different from the stars we see today. They formed from gas that contained only hydrogen and helium, with none of the heavier elements that later generations of stars would produce and scatter across the universe. Without heavier elements to radiate away heat efficiently during formation, these first stars are thought to have been enormously massive, perhaps hundreds of times the mass of our Sun, blazing with an intensity that modern stars cannot match. And they burned fast. A star hundreds of times more massive than our Sun lives for only a few million years. A brief flicker compared to the billions of years of a Sun-like star. They burned through their fuel, fused heavier elements in their cores for the first time in cosmic history, and then they died, in supernovae of almost incomprehensible violence, scattering the first heavy elements, carbon, oxygen, iron, into the universe for the first time. And many of them left behind black holes. These first black holes, the remnants of the universe's first generation of stars, were the seeds from which the supermassive black holes at the centers of galaxies may have grown. Over billions of years, through mergers and the accumulation of gas and matter, these early stellar black holes may have grown into the supermassive giants we observe today. There is also a theoretical class of black holes called primordial black holes, objects that may have formed not from stellar collapse, but directly from density fluctuations in the extremely hot, dense plasma of the very early universe, in the first fractions of a second after the Big Bang. If primordial black holes exist, they could range in mass from incredibly small, perhaps as light as an asteroid, to very large. Some physicists have proposed that primordial black holes of a certain mass range could account for some or all of the universe's dark matter, the mysterious invisible substance that makes up roughly 27% of the universe's total energy content, but has never been directly detected. The idea that the dark matter holding galaxies together might be made of ancient black holes, relics of the universe's first moments, is one of the more extraordinary proposals in modern cosmology. It remains unproven, but it has not been ruled out. The universe has been making black holes since almost the very beginning, and those first black holes may still be with us, ancient, invisible, drifting through the cosmos, remnants of a time before any star had ever shone. The universe has a long memory, and its oldest memories are dark. On the 14th of September 2015, at 5:51 in the morning Eastern Time, two extraordinarily sensitive instruments, separated by more than 3,000 kilometers, one in Louisiana and one in Washington State, detected something that had never been directly detected before in all of human history. A ripple in the fabric of space-time itself. The instruments were the LIGO detectors, the Laser Interferometer Gravitational Wave Observatory. Each one consists of two arms, 4 kilometers long, arranged in an L shape. A laser beam is split and sent down each arm, reflects off a mirror at the end, and returns to be recombined. If space-time is perfectly undisturbed, the two beams return in perfect synchrony. But if a gravitational wave passes through, stretching space-time in one direction while compressing it in another, the lengths of the two arms change by an infinitesimally small amount, and the beams return slightly out of sync. The signal detected on that September morning had been traveling for approximately 1.3 billion years. It had been generated by two black holes, one with roughly 36 solar masses, the other with roughly 29, that had been spiraling toward each other for millions of years, drawn together by gravity, orbiting faster and faster as they approached, until in their final fraction of a second, they merged into a single black hole of approximately 62 solar masses. 3 solar masses worth of matter, 3 times the mass of our entire Sun, were converted directly into gravitational wave energy in that final fraction of a second. The power output during the merger briefly exceeded the combined luminosity of all the stars in the observable universe. And the ripple from that cataclysm crossed 1.3 billion light-years of space, arriving at Earth as a distortion in space-time so small that it moved the mirrors of the LIGO detector by approximately 1,000th the diameter of a proton. 1,000th the diameter of a proton. And we measured it. The detection of gravitational waves opened an entirely new way of observing the universe. Before 2015, all of our astronomical observations had been made using electromagnetic radiation. Light, radio waves, X-rays, gamma rays. Gravitational waves are something different. They are not electromagnetic radiation. They are distortions in the geometry of space-time, passing through matter almost entirely undisturbed, carrying information about the most extreme events in the universe, merging black holes, colliding neutron stars, perhaps even the Big Bang itself. Since that first detection, LIGO and its partner observatories have detected dozens of gravitational wave events, merging black holes of various masses, merging neutron stars, and perhaps merging neutron stars and black holes. Each detection is a message from the violent universe, written in the language of space-time geometry, traveling across billions of light years to reach our instruments. We have learned to listen to the universe in a new way. And what we are hearing, in the deep, low-frequency hum of merging black holes, is the sound of the universe's most extreme events. Events that happened long before the Earth existed, in galaxies so distant their light has barely reached us. The universe has been sending these messages since the beginning. We have only just learned to receive them. When two black holes merge, they do not simply combine quietly. They ring. Like a struck bell, the newly formed black hole oscillates, radiating gravitational waves as it settles into its final shape. This ringing, called a ringdown, carries a precise signature that encodes the mass and spin of the final black hole. From the gravitational wave signal alone, we can read the properties of an object we cannot see, cannot touch, and cannot reach. Physics gives us eyes where light cannot go. Sagittarius A star is drifting in its ancient stillness at the center of our galaxy, patient, vast, and quiet. Around it, the stars of the Milky Way continue their slow, graceful orbits, each one taking hundreds of millions of years to complete a single circuit. Our own sun, with its small family of planets, is somewhere in that great turning wheel, moving through the dark at 230 kilometers per second, carrying everything we have ever known in one long, slow circle around the dark. The black holes of the universe are not frightening when you hold them gently in your mind. They are the universe's most honest objects, places where it shows you, without pretense or softening, what gravity truly is when taken to its ultimate extreme. Places where the ordinary assumptions of daily life, that time flows steadily, that space is flat, that matter persists, are revealed to be approximations, valid in the gentle conditions of ordinary life, but not at the edge of everything. Near a black hole, the universe tells the truth. And the truth is stranger and more wonderful than anything we could have imagined. Time slows, space curves, matter dissolves. Information is perhaps preserved in ways we do not yet understand, encoded on surfaces we cannot see, in a description of reality that may be deeper and more beautiful than the three-dimensional world we experience. We are made of the remnants of stars that lived and died long before our sun was born. The iron in your blood was forged in the core of a star more massive than our sun, scattered across space when that star exploded, gathered over millions of years into the cloud of gas and dust that became our solar system, incorporated into the bodies of the first living things, passed from organism to organism over billions of years of evolution, and now it is here, in you, in the dark, at rest. You are made of star stuff. And somewhere in the history of that star stuff, in the chain of stellar births and deaths that produced the atoms in your body, black holes played a role. The supernova that scattered the heavy elements across the galaxy. The stellar remnants that shaped the structure of the nebulae that gave birth to new stars. The supermassive black hole at the center of the galaxy, regulating the pace of star formation across the entire Milky Way. You are connected to the black holes of the universe, not just by gravity, not just by physics, but by the long chain of cause and effect that stretches from the first stars to the atoms in your body. The universe made black holes. The universe made stars. The stars made the atoms made you. And tonight, you are lying still in the dark, breathing slowly, your body made of ancient stardust, your mind letting go of the day's concerns, drifting toward the same quiet darkness that surrounds every star, every galaxy, every black hole in the universe. Rest now. The dark is not empty. It is full of wonder, and the most patient things in the universe are keeping watch.